All right, we are good to go. So how are you all doing today? It is not quite as cold as it felt yesterday.
Yeah.
Because yesterday it was raining. We actually might talk about rain a little bit when we do relative velocity, which we might not get to all the way today. We might save the two-dimensional relative velocity for Friday, but we'll see how today goes. But first, we have to finish thinking about projectile motion. And in projectile motion, as we discussed, our basic assumptions are zero acceleration in the x direction, which means constant velocity, which means just one x equation, and then constant acceleration in the y direction. And these equations are written the generic way with just acceleration, but I could just as easily change this. Oops. Hey, you're supposed to turn into an eraser. Oh, that happened. My tablet sometimes dies. Oh no. So first, let's deal with that. Okay. Next. There it is. So we could just as easily turn this into a minus g. So it can be plus 1/2 at squared or minus 1/2 gt squared. And then this equation can be minus g. And then this equation can be minus g. Because we know what the acceleration is in projectile motion on Earth. Yes?
What's the point of changing that?
It just makes it one step more specific to an earthly situation as opposed to being generic to any old acceleration. So each step more specific you make something makes it closer to being numerically solved. And it just happens so often that we're dealing with projectile motion on Earth because almost all people spend their entire lives on Earth. So calling it plus 1/2 at squared is very broad. It's for any constant acceleration situation. Yeah?
Okay, so I know in some equations when g is involved, sometimes it's either positive 9.8 or it's negative 9.8. How can we tell the difference?
G itself is positive. It is the acceleration in the y direction that is negative.
All right, thanks.
It's negative once you declare that the y direction is positive. And that's at the point where you call it a sub y. That's the thing that has to be negative. So sometimes what we're concerned about is the actual path through space, which you might call the trajectory of a particle. So thinking to something like Angry Birds, where do the dots appear? And for that, we kind of want to know what delta y looks like, but as a function of x instead of time. So what I want to do is I want to eliminate time from the delta y equation by using the information from the delta x equation. So this would tell me that delta t is delta x over v sub x. So I'm going to plug that in first just for the first delta t. So I have v I y times delta x over v sub x. And this is still going to be minus 1/2 g t squared. And I'm going to stop writing delta t for now, just because this makes it look a little easier. And there's something interesting right here in this fraction. This v I y over vx is equal to v initial sine theta over v initial cos theta. Because when we think about v initial, we often think about it in terms of magnitude and direction. And if you know the magnitude and the regular angle of a vector, you can calculate the components by taking magnitude times sine or cosine. So I just did it correctly for the y component in the top and the x component in the bottom. And then these vi's actually cancel. And that turns into tangent theta. That's one of that long list of trig identities. But if you're going to remember any trig identities at all, you should remember that sine over cosine is equal to tangent, and maybe sine squared plus cosine squared equals 1. And then after that, you can use tables if you need trig identities. So then I want to think about what tangent theta means. And to do that, I want to do, well, let me first rewrite the equation, and then we'll do a drawing. So delta y is equal to tangent theta delta x, and then I'm going to make this one green, minus 1/2 gt squared. So what this equation is telling me is that the actual height of the particle, that is the actual trajectory, is formed out of two terms. And one of them involves a trig function. That means that it's actually an equation for a triangle. So if I draw my x and y axes here, this blue thing here is the triangle. And there is my theta initial. This side is delta x. And tan theta I is equal to tan theta I delta x over delta x. This is obviously true because I can cancel the delta x's, and then tan theta is tan theta, that's fine. But tan theta is supposed to be opposite over adjacent. So that means that for this triangle, if the adjacent side is the plane delta x, this height is the tan theta delta x product. That's the opposite side of that triangle. So literally, whatever delta x you pick, this diagonal line represents this blue term in the equation. Then what's the green term? Well, the green term is that minus 1/2 gt squared. We've seen that before. That is the height of an object that you drop from rest. So you could imagine taking an object and dropping it from here, and it's going to go downwards to here, and that is minus 1/2 gt squared. So there's this traditional thought experiment, at least I hope it's a thought experiment, made up by some demented physicists like 50 or 60 years ago. And it involves trying to shoot a monkey out of a tree. I don't know why they picked shooting a monkey out of a tree. That's the part where I think that there's some kind of weirdo. But the idea is that the gun or the launcher is aimed directly at the target. And at the exact instant of the launch, the target is scared and begins falling. And what the trajectory equation tells us is that the bullet's trajectory, which I'm going to draw in red, is going to fall away from the blue line by the exact same amount that the target is falling. So this distance is growing as 1/2 gt squared, which means that the projectile will hit the target, and that v initial thing, the speed of the launch, is not relevant to this experiment. it canceled out here as part of this. So it could be a laser, which would practically get to the target before it had a chance to fall very far. It could be a high-speed gun, which would do about the same thing, wouldn't fall very far depending on the distances. Or it could be some kind of laboratory golf ball launcher or something like that, where the launcher is launching at some small speed and the target actually gets to fall a significant distance. Now, I would love to be able to set this thing up in front of you, set up a target up here and a launcher over there and actually do it, but I don't have the equipment to do that. So I'm going to do the next best thing, which is show you a video of it where somebody else did it. And it's only a minute long, so I'm going to go ahead and maximize this and play it. So they're showing you the launcher and the stand. So they send a guy up there to put the monkey, which I believe is like a Curious George puppet or stuffed animal, and it's hanging from an electromagnet. That allows the equipment to control exactly the moment that the stuffed monkey falls. So he's aiming it so it points directly at the target. And he's setting the launcher, setting the spring in the launcher. You have a similar launcher in lab that you're going to do in a couple of weeks. Just putting the golf ball in there. And it hits every time. So then they'll give you some slow-mo shots of it. You can see it a little better in this one. All right. So that just shows us that when we do wacky algebra stuff with math and cancel things out, that it's because there's some coincidence happening in the real world that makes that cancellation appropriate. So that launcher could be set up with a very fast launch or a medium launch or a slow launch, and either way, as long as the projectile can actually get to the vertical falling path of the stuffed monkey, it will hit.
It would just hit higher up.
It would just hit at a different spot, exactly. So a fast launch would hit up here, and a very slow launch might hit down here. Yeah, but whatever the speed of the launch, the coincidence is they're going to arrive at some point at the same time. Yeah. So one of the comments I often get from students is that I frequently don't do enough numerical examples, that I show the equations and kind of try to give intuition about the equations, but I don't do enough numerical examples. So let's do a numerical example. Yeah. So let's say that you are launching 5 meters per second at 60 degrees from a 3.0 meter shelf or table or roof or something like that. Whoops, too far. So then, to draw this, I need to give myself a little headroom at the top of the drawing. Here's our shelf, and then here's our launch, which is fairly straight up. There's our trajectory. And there's our 60 degrees and 5 meters per second. Now, since I have a vector with its known magnitude and direction, I should probably find the components of that vector. So if I think about a little diagram of just the v initial vector, it would be like this: 5 and 60 degrees. And that's what reminds me that v sub x is the adjacent to that. So that's v sub x there, and v sub y, actually iy is there. So vx is 5 sine of 60 degrees, which, by the way, comes out to 4.33 meters per second. And that's VIY, and V sub x is 5 cosine 60 degrees, which is 2.5 meters per second. Sorry, that first one is the y component, comes from the sine function because the y component is opposite to the angle. And the x component comes from the cosine because the x component is adjacent to the angle. That's what happens when I talk and write at the same time. I should probably avoid that. So then that causes the launch and causes the trajectory. And then we need to decide when to stop. Do we stop at some point up here, at the top? Do we stop at the very bottom? So if you want to know about the landing, then you want to know about this point right here, where delta y is equal to minus 3.0 meters, because that point is 3 meters below the top. So here is how I attack that. I look at I want to know delta x, which is v sub x delta t. So I know my x component of velocity because I know all about the initial velocity, and the x component doesn't change. So when I know the initial x velocity, it is the only x velocity. So I got that part of it, but I need time. I need to know what the flight time is. And I have my choice as to which of the basic equations I can use to solve for time. I don't like solving for time in the displacement equation, so I'm not going to do it. I'm going to solve for time in this equation. But in order to solve for time in this equation, I need to know more about the velocity. So I'm going to learn more about the velocity first. So we'll go down here and let's learn about the velocity. We get that from the v squared equation. V final y squared is v initial y squared minus 2g delta y. So this is 4.33 meters per second squared, quantity squared, minus 2 times 9.8 meters per second squared times minus 3 meters. So the minus sign that's part of the acceleration, I put out front here. G is not negative. I had to put the minus sign there myself. And then this minus sign is the downward lowering of the projectile from the initial point to the final point. So then this turns into 18.75, and this turns into a plus 58.8. Which is a total of 77.55. And that's v final y squared. So that means that v final y itself is the negative square root of 77.55, which is negative 8.8 0.806 meters per second. And to reiterate, I have to choose the negative square root there. Mathematics tells me that either the positive square root or the negative square root works in the equation. But the equation isn't everything. The math isn't everything. I have to apply some physics intuition to the situation. And my physics intuition is about what is the object doing at the moment it lands. It is moving downwards at the moment it lands. So that's what's telling me that that final y velocity is negative. So there's a couple of other interesting points in here. At this level here, there are actually two crossings. There's one here and one here. So this would be maybe delta y is equal to 0.5 meters. So as a little aside, at delta y equals 0.5 meters, v final y is equal to plus or minus the square root of blah, 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 blah. Same stuff to figure out what goes under the square root, except plugging in the plus 0.5 meters. And then you kind of have to decide whether you want plus or minus depending on which blue dot you're shooting for. Yeah?
Where'd you get 0.5?
I've made it up. It's a given. So if you know where the ceiling is, you would choose the height of the ceiling above the launch point. Or if you're hitting a ceiling, you're talking about the first blue dot. But if you're going up onto a roof, then you're talking about the second blue dot. So there could be like a shelf here and it's hitting the top of the shelf, or a ceiling here and it's hitting the inside of the ceiling. So the difference between the plus or minus in this version is which blue dot on the trajectory are you shooting for. So the end of that little aside. So it's actually more interesting to stop the motion on the way up because there's a variety of solutions. So anyway, now that we know v final y, I can say that I know delta vy is equal to minus gt, which means t is equal to delta vy over minus g. So I have enough information to calculate delta vy directly. A delta is final minus initial, so I plug in my final, minus 8.806, minus initial is 4.33, divide by negative 9.8 for g, and churn that through the calculator, and it should come out to 1.34 seconds, positive. And it's positive because the top is a combination of two negatives, so it makes it very negative, but it's being divided by a negative, so the signs cancel. Now remember, the goal here was to figure out the range, the delta x, and I had my Vx pretty much from the beginning. Now I have my time, so now I can calculate my delta x. So delta x is equal to Vxt, which is 2.5 times 1.34, which is 3.35 meters. So that is a complete solution, figuring out where a projectile lands. And this is basically what you have to do in lab when you do the projectile motion lab. And you have to do this over and over and over again for like 10 different angles. So definitely you want to do this in a spreadsheet, because computers are very good at repeating the same calculation over and over and over again. Now you might wonder, didn't we just go over a cool, simple range equation? So let's do another little aside. So the range equation was delta x, or the range, is vi squared over g times the sine of 2 theta, which in this case would be 5 squared over 9.8 times the sine of 120 degrees. Our launch angle was 60 degrees, but we have to put twice the launch angle into our sine function as part of the range formula. And when you run this, you get an answer of 2.21 meters. That's a bit of an issue to me, because I thought I had a nice, easy way of solving for the range. And then I did the sophisticated way, going through basic equations, but building on them, and I got a different answer. So what went wrong? Why didn't the simple range formula work?
Simple range, find simple.
Yeah, the simple formula, which we talked about on Monday, is for the special case when you're launching and landing at the same height. And here we're launching off a roof and landing on the ground. So there is a point in this drawing that corresponds to the simple range formula. It is right across here at that point, level with the launch. But that's not the point we were trying to solve for. We were trying to solve for a point on the ground. So if your destination point, if your final point is at the same level as the initial point, yeah, go ahead, use the simple range formula. And that works for kicking a ball off the ground. It works for throwing the ball from person to person, stuff like that. But if you're launching off a roof, or if you're launching up onto a roof, then that distance is going to be different. So that gives you an idea of the kinds of calculations that you can do once you understand projectile motion. And remember, all of that came from the combination of two basic ideas. One, using constant acceleration, and that exploded into a whole bunch of kinematics equations. And the second idea is the idea of a vector velocity, where we can start with a magnitude and direction and then split into components and then do kinematics. So this is a big example from this first unit of the course, and I guarantee you there's going to be some projectile motion on the test, which I think your test is going to be next week. Yeah. Should we have it Wednesday or Friday? Friday. That seemed fairly unanimous. In fact, I don't think I heard one person say Wednesday. I almost feel silly for asking. All right. We have one more new topic to go over, and we'll do some of it today and probably some of it on this Friday. And then next week we'll spend reviewing. So the thing we have to talk about is relative velocity. History. Hide authors. There we go. And relative velocity is used in several different scenarios. Sometimes it's used when you're tracking two different objects. And sometimes it's used when you have one object that is moving inside a medium. And that could be a boat moving in some water, or a plane flying in some air. It could be a person walking on one of those moving sidewalks, or a person walking on an escalator. And the idea of relative velocity starts out with a nice, simple mathematical idea that relative velocity, which is here, is equal to the ground velocity minus, actually, let's not call that ground. Let's call this, let's call it actual. So your relative velocity is your actual velocity, like measured relative to the Earth, measured relative to things that everybody agrees that we care about, minus the velocity of your medium. So there's a bunch of different scenarios we can deal with for this. And the easiest one is to think about upstream and downstream. And some examples of cases that this might apply to would be a plane that's flying directly into or with the wind. Swimming upstream or downstream, or walking on a moving sidewalk. So usually when we deal with these situations, the first introduction is thinking about a boat in water, because for most people it's easy to imagine standing on the land and it's easy to imagine standing in the boat, and it's fairly straightforward to think about what it's like to be in the water. So if we take a river, and let's say we have some V water, and we'll make this 3 meters per second. And then think about a person trying to swim in this water. I may have made the water too fast, but that's just too bad for the person. So if they are moving downstream, so we're talking V person relative to water is equal to V person minus V water. And let's take all x components. And by declaring that I'm taking all x components, it gives me the ability to, first of all, stop writing arrows over top of my variables. And secondly, it gives me the ability to choose which things are supposed to be plus and which things are supposed to be minus. So this ability of a person relative to the water might be, let's say it's a very fast swimmer, 4 meters per second. Maybe they actually have a small jet ski or something and they're driving it slowly. So that number would go here. So that would be 4 meters per second is equal to V person minus 3 meters per second. So the relative velocity, the person, goes in there in the spot where there's 2 indices in my notation, and the velocity of the water goes in here. It's not minus because the water's negative, it's minus because that's the definition of relative velocity. A relative velocity is a subtraction of two regular velocities. Now, usually when you solve this, like for here, we know 2 out of the 3 variables. So let's move this over to the other side, which you do by addition. So V water plus V person relative to water is equal to V person. So 3 meters per second plus 4 meters per second is equal to V person. So the result of this is probably something that may have been intuitive to you. If they swim downstream, the water gives them a boost. It makes them go faster. And how do you calculate how much faster it makes them go? You simply add the speeds. So you find that they get to go 7 meters per second. Now, if on the other hand, you go upstream, then that means V person relative to water is equal to minus 4 meters per second. It is their relative velocity that automatically reverses when they turn the other way. So then we have V person is equal to V water plus V person relative to water is equal to 3 meters per second plus minus 4 meters per second is equal to minus 1 meter per second. So in that case, it ends up being a subtraction of the speeds. And just imagine swimming against the current, going against the flow. It's fighting you, and the way you calculate how well it fights you is by subtraction. Now, when you subtract numbers, there's a possibility of the result coming out positive or negative, and whether it comes out positive or negative depends on which one of them wins. So if, as in this case, the person can swim faster than the current, then they're going to win, and the ultimate speed relative to the ground is actually going to be upstream. They're going to get to make progress. If, on the other hand, they are a slow swimmer, like me, then they would be swimming against the current, but the current would just carry them backwards. So then they would not be able to actually make progress against the current. This idea of trying to swim against the current but failing is actually kind of a big deal. Whenever there are what are called rip tides or rip currents out in the Gulf water, frequently that current is flowing out to sea faster than a person can swim. And if a person attempts to just directly swim to shore, if you say, I want to be over there, I'm going to swim that way, then the danger is that the current will carry you out to sea faster than you can swim inward. And then you'll just keep swimming and swimming, not get out of the water, and get tired and drown. So the solution is don't do that. Swim sideways instead, because the current is carrying you out, and swimming sideways will still allow you to make a form of progress. It would allow you to get out of the current, which would then allow you to find a different place to swim towards shore where you can actually do it without the current happening. Now, we're going to deal with the two-dimensional cases, like the swimming sideways relative to the rip current or trying to swim across a river or something like that. We'll deal with that Friday. I want to look at the timing of swimming upstream and downstream, because The velocities simply add and subtract, but the times do not. So let's take the same situation and we'll consider a 120-meter journey. So for the walking person, that is somebody who's not subject to the current, you would just think of delta x is equal to Vx delta t. So delta t is equal to delta x over Vx is 120 meters over 4 meters per second is equal to 30 seconds. So that's the kind of calculation we did on the first or second day of class. If you think about just the water by itself, the water was moving 3 meters per second, so then you get delta t is equal to 120 meters over 3 meters per second is equal to 40 seconds. So if you threw a ball into the water, it would take that ball 40 seconds to flow downstream 120 meters. And if we swim downstream, that was V person is equal to 7 meters per second. So then delta t is 120 meters over 7 meters per second is equal to something that I have to calculate. 120 over 7 is 17.1 seconds. And if we swim upstream, then V person is 1 meter per second, and delta t is 120 meters over 1 meter per second is equal to 120 seconds. So you can see pretty clearly here that even though we're adding and subtracting velocities, when you compare journeys of the same distance, you can't just add and subtract the times. Probably the best thing, the easiest thing to do is just to plug things in and calculate them directly. So do add and subtract the velocities in a relative velocity scenario. When you need the times, you just need to calculate those. Now, let me just do one little thing about the idea of river crossing, because I know some of you are working on the homework 2 to try to finish it by tomorrow night. River crossing is inherently a two-dimensional relative velocity situation. And of course, you can make your drawing any way you want. I think in our homework questions, the river is left or right. So I'm going to make my drawing like that. And we'll have V water. And then let's have V person relative to water. This person tries to swim straight across. So in navigation, I believe that there's 2 words that are relevant to this situation: heading and bearing. And a heading is where the nose of the person or the nose of the boat or the nose of the plane points. and they're pointing in the y direction. But the bearing is the actual direction to some actual object or destination. And in this case, as they try to swim straight across, the water's going to carry them downstream, so their bearing is going to end up being diagonal. And what you basically have to do is separate it into x direction and y direction. So you start with v person relative to water is v person minus v water vectors. And then you say x direction, v person water x is equal to v person x minus v water x. Now we can think about values that might go in here. As drawn, this is 0, is, let's give a number to the v water, 3. So because the person is heading in the y direction, they have no x component relative to the water. But because the water is carrying them downstream, they end up having an actual velocity x component that is, that's supposed to be v. I don't know why I wrote velocity as a letter p. So we end up with v person x is equal to 3. And then in the y direction, v person water y is equal to v person y minus v water y. So this is the 0 in the y direction in this scenario. And what we find is that if the water's in the x direction, the water doesn't affect their y direction velocity. So their y direction velocity is the same whether we think about the relative velocity, which is their effort, or the actual velocity, which is their progress in the real world. So just remember that this one is effort or heading, if that word means something to you. This is ground progress or bearing. Now, this drawing is the simplest possible drawing, and we'll go through a numerical example of this on Friday. But of course, the person is allowed to give themselves an x velocity. They can direct their swimming. So what can change in this analysis? This might not be 0. So think about what you know for sure, figure out where it fits into the basic equations. Then you can start dealing with vectors and directions and stuff. All right, I'll see you guys on Friday.